All right. Now we've reset the camera, obviously, so that we're basically having the camera have the effect of being straight in front of the diagram where I was before. It's a little further back. You know, I was about here, but because of the way the lens works, it's actually, we need to bring it farther back to see about the same thing we were before, or I was. We're a little behind our own cone now, but that's fine. I've also raised the ground level to this table, so we can consider the tabletop just like a second ground level or the ground level now. Instead of being down there, we're up here. And that means, as we discussed in the diagram before in part 3, or in the previous lecture, physical lecture, we now have the ground plane meeting the picture plane here, and we can consider this a ground line meeting the picture plane and continue on that way and this way to be a measuring line. And we could measure all this in the whole perspective, because what you're seeing here is very real to what we could do. The cube is in front of the picture plane now, obviously. It could also be back behind it. We could go way back with other cubes back here to eventually that got so small near the horizon line, eye level, we'd never see them. A whole grid could be measured. Things could be brought forward more into space here. We could do anything we want. So we're just having a cube, an actual cube, slightly in front of the picture plane for the same illusion to make some points about how we know and why we are in 1-point, 2-point, and 3-point perspective now. So we'll use this simple object, the cube, to explain that, and hopefully that will help you visualize as we go into the diagrams why we're looking and seeing and talking about what we are. And also, if you get confused later, it would be really helpful to probably come back to this idea. So even if we're in the middle of the diagrams many, many lectures from now and you still are not quite understanding why something is, it might help you come back to the physical lecture with a real object with me kind of moving around and acting out why it works. So that's the reason we're doing it. Okay, so this cube is in 1-point to you, the viewer, now. So it's all about you and viewer-centric from the camera now. We're in 1-point to the cube because this plane and the back plane aren't in perspective. They're parallel with the picture plane, and the sides are perpendicular. And because the sides are perpendicular, the sides go back to that vanishing point, or should. If the camera was perfect in view compared to this, like a drawing, these should diminish exactly and go back to the 1-point vanishing point, of course, which is always on the eye level at the point of the center of vision. So again, even if we had diagonals drawn across the plane of this cube, they would have no diminishment or no perspective to them, because they would come straight down at real angles, because this plane has no perspective. It's flush or flat to the picture plane or parallel to it. And so same with the back, same with the table at this point as well. So again, that's why we know we're in 1-point. So you could be looking at a photograph with many, many, many objects, and as long as you're identifying as many of them or most of them in your design, you want to have this effect that the front plane and the back plane and all those planes are parallel to the picture plane. Then you know you're in 1-point. And of course, again, the perpendicular side planes would be going to the 1-point vanishing point, assuming that things are flush or standing on a flush ground plane. If they're tipping, that involves auxiliaries, which I'll explain in a minute. Secondly, it's important to understand that all verticals, when you're standing normally on the ground, are going to the core of the earth, essentially. They go way, way down all the way to infinity, but in that case, they're passing through the core of the earth, which is important. So any true vertical standing on a flush ground plane, perpendicular to it, we could consider going to the core of the earth, which is important because it kind of embeds it in your mind of like, oh yeah, right, true verticals are always straight up and down. Perfect, okay. Again, this is look at how foreshortened that becomes. So imagine if you think there's really long squares coming toward everybody in perspective, look at how foreshortened this actual square is on the top plane to your view of the camera. It's actually pretty foreshortened. It's surprising. The further it moves up toward the horizon line eye level, it will become more and more foreshortened until it just disappears and becomes a flat line up here. So we know we could get down a little further in our cone view from this, and then this would become broader. But again, the main thing is, if we know these are flush to the picture plane and these are perpendicular, behaving to this vanishing point, we know we're in 1-point, or we can create it so in a design, okay? The odd thing about when you go slightly into 2-point, sometimes it's better just to adjust your design to be in 1-point. It can be a more powerful idea. For instance, this cube is no longer in 1-point, but it's so close, you're like, well, it's almost annoying what a tiny angle that is. So if you redraw things or you redesign them anyway, from your own artistic skill, your viewpoint, the way you wish it to be, you might decide that things that are barely in 2-point might as well just be brought back to and be in 1-point, because it might be just a stronger design and less confusing for the viewer if they're so close to 1-point anyway. Another thing is 1-point, we're still in 1-point if this just slides back and forth or up and down. So if I go over here with this, still in one point and behaves to that vanishing point, and this still has no perspective. If I slide it over here, same thing. This still has no perspective, neither does this plane. These are still perpendicular to you and should be going to that. No difference. We're just sliding it back and forth till it disappears out of your cone or completely out of your frame. Okay? That's important because no matter what, or up and down, by the way, I don't want to forget to mention that, as long as this is still straight towards you in the same manner, it can go anywhere around here, floating. That's still all in one point and will still behave to that vanishing point and be having no perspective on this plane, okay? So one more thing about 1 point. Well, we'll talk about auxiliaries actually altogether. Let me skip that. Let's go to 2 point now. Why do we know we're in 2 point? Because suddenly we're not in this position anymore. So I'll turn it slightly like this. That's not even. There's much more length to the vanishing point to our eye level this way than there is here. This one ends up about here. Why do we know they go to the eye level picture plane? Or typically the horizon, because we're still on flush ground here, and that means that their vanishing points for these planes will end up somewhere on that eye level, on the actual angle they're striking out toward it. The other one would be about here. The interesting part is, because this is a true 90, if we were looking from above, like when we have our flattened SP, you can project a real 90 at these same angles as here, longer, shorter, same angles from your station point. That's the flap that we talked about last time, because that allows you to have these angles in your picture using the station point that's flattened out will travel and strike the same vanishing points this real object would. That's the whole point, is because the flattened station point that did represent this one that has been flattened, like we talked about in the last parts, that will allow you to take the real angle and situation this is to the center of vision as a flat idea and project up and hit the same vanishing points as this actual diminishment does, landing here and way out there. That's why the flattened station point is so useful and helpful. Okay, so now we know that the cube can be turned more. So this is more 45 and 45. That's more even, roughly, from your view. I'm just guesstimating. But then we could say 45 and 45 because it breaks the 90 in half. So now if we were to take it down to that flat SP or look at it, it's about even. And that would be true when you project from the 45 and 45 from your station point, only meaning that you get a, kind of a centered look to your cube in 2 point. Still flush with the ground plane. Verticals are still all, they're still all traveling straight up and down. You can still move this over here real quick. We can still go up and down, no problem, as long as it's still straight onto you at the same angle, and I haven't turned it like this, I'm just doing this. That will still use the same vanishing points the whole time for the cube. Verticals are straight down into the earth, and I haven't changed the direction of those side angle vanishing points at all, okay? Turn it like this, all different directions. I'm just turning it in different vanishing points, which will in fact be closer and farther out as I change the angle. So as I do this, those vanishing points are going way out there and then coming back, and shallow here going way out there. That all changes each time you change that angle. So we know we're in 2 point when we no longer have any of the planes of the cube facing the picture plane flat. We know we have true verticals if we're still in a flush ground plane, but now we know that these certainly aren't facing flush to the picture plane or you, the viewer. Therefore, you have to lead some way back to get a vanishing point, way back here off camera to get a vanishing point. Because the ground plane is flush again, we know those vanishing points appear at the point of the eye level horizon line, okay? Let me think. Okay, we talked about moving it around. Again, doing this, they stay the same as long as they don't turn. So now let's talk about 3 point perspective. 3 point perspective, we'll go back to the simple view of this. 3 point perspective now is when we're not changing our view at all, we're just changing the object to us, but it's in a sense you can still describe the same effect. Later in the next segment we'll talk about actually changing our view a whole bunch, but right now we're going to stick to this. So 3 point. We're still in 1 point perspective, and as long as I tip just straight toward you, the viewer, because we're perpendicular and parallel to the picture plane, then what happens to the verticals, these which were going into the earth now, let's just take it and flip it down. As long as I'm tipping it straight toward you, these same verticals now actually take and reach a vanishing point way down or closer to, for more severe, on the center of vision. So less tipped, further down, they diminish to a single vanishing point called a vertical vanishing point in 3-point at the center of vision. And more severely, they'll be much closer up this way because these converge even steeper and they come up the center of vision closer to the eye level on the picture plane. And again, very severely, they'd be very close, just below the table if you did that. That is basically tipping down and looking at the top of things, which is typically called bird's eye. Worm's eye is the opposite. Now we'll tip it up toward this. Now the verticals are going up and up and up and diminishing to a point above the eye level on the center of vision line. And why does that vanishing point happen on the center of vision line? Because we're agreeing to tip it straight up and down like this toward you or away from you. We're not turning it yet. That will be a different situation when we turn it and would become auxiliary vanishing points for slopes and inclines, which is weird. They seem like the same thing, but they're actually different. Okay? So again, bird's eye from above, tipping back straight toward the camera, back toward the picture plane. Worm's eye view, vanishing point for the verticals, goes somewhat or very up or a little up on the center of vision line to create a vanishing point, a vertical vanishing point for the verticals. Okay? Now, we'll turn it like this again in 2-point. Now, verticals going straight down to the ground. Now, if I tip this, I have to tip it again straight off the balance point of this front corner, straight toward the camera, or in the back corner, straight back toward the picture plane in order to keep the vertical vanishing point, to keep it appearing on the center of vision line. Otherwise, it's going to kick it out somewhere else and become something different. So I'll just try to imagine these verticals are going straight into the earth now. If I tip it straight toward you, without tipping this whole little table over, which I'm about to, these verticals, all 4 corners that were the verticals now, these 4 planes, go down to a converging vanishing point somewhat under the table on the center of vision line, just like they did for the 1-point situation. If I tip it back, same thing. If I tip it straight back toward the picture plane, these verticals still tip and converge to a point up there on the center of vision. Again, so that would be bird's eye and worm's eye 3-point with a simple cube. We're not changing our angle of view, we're just changing the cube, so it's at a different angle of view to us, but we're staying the same with this whole basic setup here. That's inherently different than what we do when we have auxiliary vanishing points. And again, I don't expect everybody to even understand this exactly now. This is really for a reference point when you get confused later or have questions and refer to other material. You can go back to this physical lecture and say, okay, how does that match up with what I was talking about in physically demonstrating this in this same perspective setup that very closely matches how you'd set up a perspective drawing, especially when you include all this information. Then you can match it, and maybe you can confirm, yes, that's correct, I'm doing the right thing, because this source here says it, a later diagram might say it, but also this confirms it, the kind of behavior. So let's take the cube again, now in 2-point, and say, let's say we don't tip it straight forward toward the camera or straight toward the back toward the picture plane. Now, if we're talking about these angles here on the cube, if I tip it this way, the interesting thing is that these were going all to that vanishing point over there on the horizon line. Why? Because this is a flush ground plane, the cube's flush with the ground plane, and so therefore, the vanishing point from the planes will go back and hit somewhere over there. The interesting thing is if I still mark that vanishing point on the ground plane and I tip this like this, these angles all converge to a vanishing point that is drawn directly under that traditional ground point vanishing point, and that's called an auxiliary vanishing point for inclines. And this, in fact, is a decline. So you could say this is a declined auxiliary vanishing point. That's how that behaves, but if I do this, it's the opposite. You would go to a vanishing point that goes up and converges straight above the ground plane vanishing point that appears there. Because I tip it straight above that with a line, these converge to a vanishing point straight above that on a line and called an auxiliary incline vanishing point. Okay? Same here. If we do it in this direction or we do it in this direction, then we'd come over to the ground plane one over here, and if we tip it up or back, the same thing happens. If we went down, then it would go down toward here, and if we went up, it would go up toward the vanishing point this way. Same thing. That's incline vanishing point. So again, down toward this, with a line below it, would be a declined vanishing point, auxiliary vanishing point. Oh, incline somewhere up here. Incline, I don't want to tip the whole table over. So again, confusing now. I know it's a lot of information, but I only have, I want to explain as much as possible so people can refer back to this physical explanation in different parts. So it's not like you have to take the whole thing in at once. You'd want to refer back to this lecture or this entire lecture 1 as you need to when you come to areas in the diagrams or other drawovers that you become confused by. This physical lecture of the entire thing, parts 1 through 5, would be helpful, okay? So again, that's pretty much it. Let's see if I've left anything out. Oh, we're going to bring a little cylinder up here too. But also, draw a lot. Obviously, if some of you haven't drawn much, then just draw a lot of different objects that are like rectangles and things in still eyes from all different angles. You'll really see these concepts as we go forward with the diagrams and the more technical perspective. You'll see these concepts come alive all over the place when you're drawing. And again, it's critical to draw from observation. This lecture series is mostly about why perspective behaves, but again, as I mentioned before, it's critical that you're matching and pairing that with your physical observational drawing skills and your knowledge of the world from that standpoint. It's critical, okay? So we'll bring, I think that's all I wanted to say about the cube. Yeah, so let's bring up the cylinder and a cylinder. Okay, so if I brought this look at how foreshortened that is as a ellipse, okay? It's flat up here. As I turn it, obviously it becomes more of a real flat circle right up there. Turn it more flat. When we bring it down, more foreshortening. Also flat, flat, turns, ellipse, 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 straight on, turn. Real simple stuff. We'll learn all about ellipses, technically how to create them, why they work, why the illusion of a perfect oval with a line in the middle appears to be also a circle in perspective. They're the same thing. We'll talk about all that stuff. But I wanted to make you aware of, again, be clear about the fact when you're trying to learn and construct ellipses in your kind of in your imaginary drawings, when you make them up and try to construct them or are constructing them, think about taking an object like a soup can or anything and keep turning it like this and really draw from it to help you understand where is the major and minor, why do they happen according to the diagrams. It's very helpful to draw real objects, obviously, and practice that way. Pretty critical there. Okay, great. So next we'll just do a little bit of reviewing how we change angles all over the world in an infinite way by changing our view with the cone of vision and stuff as we walk around the room or spin around the room a little bit. So in this case, we changed the angles of a single object and kept our view the same and didn't move. The camera didn't move. Next, we're going to talk about how to be the station point viewer and then move all over the place and what perspective we'd actually be looking in, much as the same way we described what perspective we were looking in when we changed the cube and a little bit with the ellipses here, okay? All right, so we'll see you in a bit.